meaning what do you do with the land and how that land may affect your quantity and quality of the water. Okay, it's mainly analyzing the landscape of your watershed. Okay. What do you do? The human-induced impact, whether that can be land use change, land management change, climate, or it could be water quality. Okay. So one of the fundamental principles that we started at the beginning is we don't want to develop a model for the sake of developing a model that's going to be used only for very few people, right? Only our research group or our students and our collaborators. But we really want to make this available as widely as possible, actually. So one of the fundamental focus we have is what is available, actually. If data is not available, nobody's going to use our model. If you develop a model so complex that you need to go out and collect data before you can apply that model, nobody is interested in that model, actually. Okay, not everybody can go and collect data. Not everybody has got the time or effort to do that. Because if you're doing a master's, a 2-year program, PhD, 3 to 5 year program, you won't have the data to do that. So that means you have to make use of existing data that's already available, that's already collected. And how can you use the data to develop a model, rather than going and collecting the data and applying. You can do that, but you may take more time actually to do that. Okay? But that doesn't mean we only use readily available input data actually. Sometimes we also adapt. Our model has been changed over the years to use satellite data. Okay? So if you look at our model started in 1990, at that time the satellites were not popular. Okay? But today satellites are very popular. There is more data available through satellite media. Right? So we are starting to adapt to the data that's coming from satellite as an input to our model or as a verification to our model. I'll talk about some of those concepts later. Our model is also physically based. What I mean by physically based, meaning it's spatially explicit. Your landscape, later in the slide I'll show you how you can divide your landscape into land management unit. Okay? So it is spatially explicit on the landscape to capture the rainfall, runoff, vegetation, and soil processes. Okay? The two message, if you take home message from this presentation today would be how comprehensive is the SWAT model, meaning how you could potentially able to look at the various aspects of land management and the interaction of the land management with various processes in the natural processes that's happening in the real world, and the simulation of alternative management, meaning simulation of scenarios. Okay? How can you run different scenarios to look at what if? Okay, what happens if I change my land use from agriculture to pasture, or pasture to forest, or forest to urban? So how that's going to make an impact on water quantity and quality, for example. Okay? So you are developing a model such as SWAT is not to prove the model works actually. Yes, you do need to do that to gain confidence in your model, but the main reason that you develop model is to run alternative scenarios. Okay? For example, if Anna wants to put a monitoring station, where is the best place to put the monitoring station? Right? If you want to put a meteorological station, where is the best place to put a meteorological station? Where is the gap, data gap, for example? Okay. So one of the PhD students in Belgium, she used the SWOT model and advised the government of Belgium to know where to collect data for pesticides. So their interest is water quality, drinking water quality actually. How good is the quality of your water by measuring pesticide in the river so that they can be able to identify what are the health risks. Okay. So to do that, pesticide is very expensive to collect data, to analyze data. Each sample costs more than $100. So that means there's only so many samples you can collect. So she used the model to identify the locations where you can collect data, how many times you have to collect data, when to collect data, where to collect data, and what to collect data. So you could answer, the model can be useful in this manner to set up an experiment, okay? So that you can look at the spatial and temporal variability and try to capture that and able to simulate the land management based on the impact of what's happening. Because the land is changing constantly. It's not constant. Your topography may be kind of constant. Your soils kind of constant, right? It's not changing unless you change the topsoil or things like that. But your weather is changing, right? Your temperature, your precipitation events will change. Your land use will change actually. So the main driver for any land management is going to be weather and land use. Okay? Your elevation and soils are not that dynamic. They may change once in 50 years or once in 20 years, not from year to year. Whereas weather and land use will change almost on a yearly basis. Okay? Land use maybe once in few years, maybe once in 3 years or once in 5 years, but weather every year changes. So that's what we are trying to capture is the variability of your landscape and how that might impact your quantity and quality of your water. Okay. Stop me anytime if you have any questions, okay, please. So one of the fundamental philosophy is that we want to develop the model with a simple understanding. Okay, we don't understand everything what's going on actually. It's the real world is very complex, right? So what is model? Model is the simplicity of abstraction of reality. We are trying to capture the real world processes through mathematical formula in a computer simulation model. But we may not know everything what's going on. The mother nature is very complex, right? So we try to capture the best of what we understand and we make assumptions. We make unknowns, right? Like constants and coefficients and things like that actually to represent the process, but that doesn't mean the model is perfect. Okay, model is always opportunity to improve as we gain new knowledge. Okay. So we try to keep it as simple as possible, but still follow the law of physics and chemistry. Okay? So we can't change the law of physics and chemistry to make simulation models. So we still use those in our process. These are all the different models we have developed over the years in our research center. In the 1960s, the universal soil loss equation, this is just a plot. It's not a model, it's just a plot study that when we measure how much is the erosion, how much is the sediment is lost from the different agricultural management practices. Based on topography, based on soils, based on rainfall, based on the type of vegetation, it's simple measurements to quantify how much is lost. The very first computer simulation model was around 1972. It's based on a law that was passed in the US called Clean Water Act. Okay, how to protect your water resources. So they realized it around 1970, 72 to be precise, on what do we do about the quality of the water, more than quantity of the water, because you can have all the quantity in the world actually, but you can't, if the quality is not good, that water is not going to be good either actually. The amount of resources you have to spend to clean that water is not going to be worth at the end of the day actually when you need to use that water. So protecting your quality of the water at the source. Source meaning where it is produced. When there is a rain, and that rain is going to produce runoff, right? At that source itself, you have to protect your quality of the water. If you don't protect it there, it's not going to be that great when it comes to river or in the lakes or in the ocean and things like that. Then in the 1980s, we had a model called EPIC. And then in the 1990s, we had a SWARM, and then eventually this is converted into SWAT. Even today, this model 1980s developed model EPIC is the most used model in the world actually. If you look at every model in the world, this is the most used model in the world actually. Okay. But it is a field scale model. That means you can look at one field at a time. It is not a watershed model. It cannot go both space and time. It's just looking at vertical one-dimensional model. Okay. Then whereas SWAT is a landscape model, watershed model, it goes across the entire watershed. It can be as big as the entire Amazonia basin, for example, or the entire Parana River actually, or Para River. So you could be able to simulate the watersheds of any size. Again, it depends on the details of your data, how detailed you want to model versus how less detail you want to model. It depends on the question that you are asking. Okay. So 90% of the modeling is based on what you want to know from the model. Okay. If you know what is the questions you are trying to answer, then your problem is mostly solved. It's not knowing what you want and then keep changing it, because just to give you an example, I'm working with a lake manager who supplies water to the city of Dallas. Okay. He supplies 4 million people every day with the lakes. They manage 5 lakes in and around Dallas Central. So I started working with them around 1995, and I'm working with them even today. Okay. You could ask me, why is it taking 30 years to develop a model for that, say, 5 lakes actually? It's not that thing. We developed the model within a few years, but they keep asking more and more questions, different questions. And the data is evolving. As we find something, there is a data gap. There is a knowledge gap. So we go back to the drawing board, we go back to them and we say to them, okay, we need this data. Or we need to collect more of data for this particular time period of the year, because that's a rainy season or non-rainy season, things like that. So as we ask for more data, they go and collect the data, then we go back to modeling again, we develop the model, apply the model, answer the question. So like that it's been continuously going on for the last 30 plus years. So model is what is it that you want from the model and what questions you are trying to answer from the model, and how do you have enough data to answer that question. Those are the things that's going to take time or resources to develop model. We also have a few other models like these that you show on the bottom here. Some of them no longer exist. One of the sad story on model development is when the model developer retires or when he passes away, the model dies with the model developer. If there is not a caretaker, if there is not a big organization behind that actually, normally it goes off actually, it doesn't survive. So, like for example, Gleams, when the author died, the model didn't die also. So, but we took the best science out of the Gleams and incorporated both in EPIC and SWAT. Gleams is a pesticide model. It is developed for pesticide movement. So we took the pesticide component from the Gleams and incorporated in our models. So like that, we take the best of each model where it is available and then try to integrate that with our model. So when those models become obsolete, our models can still be able to carry on. So one of the things that we are working on is to making sure we have succession plan, meaning when we retire actually or when we go away, there will be somebody else to take care of that. So we are working on succession plan. So we already started 10 years ago. So if you know that somebody is going to retire 10 years ahead, we started that plan and we have somebody now taking care of the EPIC model, and we are working on our succession plan between myself and Dr. Jeff Arnold. We two are the main working with SWAT model. Jeff is planning on retiring in another 5 years. I may retire in 10 years. So that means we need to have somebody to come and take care of that. So we are working on that transition plan right now. So these are the 4 models that we currently manage, maintain, actively do research today. EPIC, which is a field scale model like I mentioned. Almanac is also a field scale model. Almanac is mostly a research model. It is not a practical tool actually. This is a researchers uses that model to develop parameters for other models. Okay. It's much more primitive. You need a lot of field data to operate that model, Almanac model. Okay. So it's mostly used only by the scientists, not by the practitioners. Then the apex is a farm scale or a micro catchment. When I say micro catchment, I'm talking about something like 5 to 10 square kilometers. A very, very small catchment. If you want to model that, then you can use the apex model. But apex requires a lot of data. It's much more data intensive than SWAT because you are capturing every field by field by field actually within that micro catchment. So that means you need obviously more data. So there are experimental watersheds that you may have data, something like that. Then in that particular situation, you should be able to use apex. The only thing is you can't scale it up to very, very large scale, like a river basin, for example. And finally, the SWAT. SWAT is a watershed scale or river basin scale model. Actually, you can model all the way from few hundred acres to thousands and thousands of square kilometers. Okay. That doesn't mean it is less accurate or more accurate at any particular scale. The scale is dependent on your quality of data. If your quality of data is really, really good, you can capture very few small area all the way to thousands of square kilometers. Because just an example, for example, so if you have a 1,000 square kilometer watershed and you have, let's say, about 2,000 farmers managing land actually, everybody is going to manage differently, right? So if you have, let's say, sugarcane field, not everybody is going to plant on the same day. Not everybody is going to apply the same amount of fertilizer. Or not everybody is going to harvest on the same day actually, right? So knowing that detail, not only that actually, if you are simulating for 30 years of time period, we don't know what happened 30 years ago or 25 years ago. How did they manage the land? How are they managing it today? So that kind of detailed information is very, very difficult to obtain. So we have to make a lot of assumptions, a lot of experts' opinion, okay, or a lot of survey, or a lot of interaction with the farmers to find out how did his father or his grandfather did the work in the field actually, and what are they doing it differently now? Did they have yield? How much difference in the yield? If you look at in the U.S., as you know, corn is the major production in the U.S., right? If you go 1960, the average corn produces only about 4 tons per hectare. Okay. Today, same field, same location, producing 12 to 15 tons per hectare. The yield has increased 300%. Right? It's same land, same area, it's only management. The seed technology has improved. The management has improved. When to plant, how to harvest, and also the fertilizer input, the knowledge about how to manage the plant or the field has changed actually. So I mean, that's a revolution that's going on throughout the world actually. It's not just the US. Everywhere is changing, everywhere is improving and increasing and things like that. The same cornfield in Africa, for example, still producing only about 1 ton or half a ton per hectare. Because the inputs, the cost of input, the knowledge of managing land is still not lacking significantly. Okay. So knowing that exactly how the land managed and what information is needed to build a model is key. So that means talking to your land managers or land owners and the farmers is very important. Okay. So I know there are a lot of experts that you could talk to and gather that kind of knowledge before you set up a model like SWAT.
Professor?
Yes.
Yeah,
Please.
So if you talked about the amount of data that you need when you want to model a small region.
Mm-hmm.
So if you are talking about 50 or to 100,000 kilometers region, a small city, and you want to build a model for this region to forecast floodings and things like that, how much data you need how many stations and how big is the length of the data that you need for a region like that? You know it from,
I mean, I know you said 50 to 100,000 or 50 to 100 square kilometers.
50 to 100,000 is
Square kilometers. I mean, you're talking about 50 to 100. That's a large area actually.
Yeah,
It's a very large area.
okay, so keep on 50.
Okay, 50 to 100 square kilometers may be more like it for your city actually, small city.
Yeah.
Okay, so like the one that we are here, it's 50 square kilometers is still a very large for this city here actually. For here, did you know it could be very much
Make
bigger.
it small.
Yeah.
Okay.
So, I mean, the data, it depends on where you want the answer. Okay, how detailed you want the answer actually. Do you want the answer to be for every kilometer, every square kilometer? Or do you want the answer for every 5 square kilometers? Okay, so it depends on what questions you are trying to answer and where and when you want that answer. That dictates how much data you need actually. How detailed you want the precipitation. How does the precipitation changes? For example, in Texas, I may be only 3 kilometers away from my office. It may rain in my house, but it may not rain in the office, right? So the rainfall changes. The spatial variability of rainfall changes. So how you capture that? How many precipitation stations do you have data for actually? Okay. So nowadays we use radar. So we cannot gauge every location, right? So we use radar to capture rainfall. So when you look at the pictures in the TV, you see the rain passing through here actually. So that's a radar image. It's a remotely sensed product. Okay, so we are not collecting data for every pixel, but we are using the radar to collect the data actually. Sometimes radar has problems. For example, one radar may cover a region of about, say, 1,000 square kilometers. So what happens is sometimes if there is birds fly around, so the signal that goes there actually, it hits on the bird, that means it's going to reflect back to the radar. It thinks there is a rain going on at that location. Okay, so just because it's radar data, it doesn't mean it's perfect. There are ways to clean the data. There are ways to improve the data source or things like that. But regardless, the amount of data requirement depends on the question that you're going to ask and where and when and how much. I would never say not to model actually, meaning don't wait for the perfect data set. There is nothing called perfect data set actually. Okay, so you have to use what you got because you are not going to go back in time to collect data. You can plan for future data, but not what's happened in the past. So that means you have to use the data what you got and try to build a model the best you can, and then try to explain, say, what is missing. Okay, what can you or what you cannot do with that model. Okay, if you want to do these other things, what else data you need to collect? Okay, so it's an iterative process. Okay, you need to do something in order to know something, and then when you know something, then you can go back and collect more data. And then you do that over and over again. Just like going back to the city of Dallas people that I'm working with, where I'm working for 30 years, it's not just one-time application. It continuously evolves, continuously changing over that period. Yeah. Any other questions or comments? Okay. So one of the things that this model is, SWAT model is very popular is because of the conference and the meetings that we conduct, like workshops and things we conduct actually. We started our first conference in 2001 in Germany, and then we used to do every other year in Europe, but now we are doing every year. Now we are doing 2 conferences per year actually. Okay? So please feel free to join us in any of this conference. We just had a conference in Denmark, and next year we are going to have one in France, and that's the 2024 Olympics. So we are doing the conference just 2 weeks before the Olympics. So if you come there, you can also stay there and participate in Olympics, watch Olympics. Next year we are also planning one in Lima, in Peru, next fall, in September, October time frame. I think most likely in September. We are planning one in Lima, and we are also planning one in Morocco actually. So depending on where you want to, which are the places you want to go, you are welcome to come and join us in any of the international conference. So SWAT is a daily time step model, meaning it takes your daily precipitation and looks at your land use, the soil and the topography to estimate how much runoff, how much pollutant, or how much is the pollution from those runoff attached to that water. We also have sub-daily or hourly simulation model. Okay? For that you need hourly precipitation data set. You can't take the daily rainfall data and try to run it for hourly, because we don't know which hour the rain really happened. So let's say you had a rain yesterday, the rain happened from 6 to 7 o'clock in the morning. We won't know that if you don't capture that time of the rain, the intensity of the rain, whether you had the rain of 30 millimeter or 50 millimeter in half an hour, or 30 millimeter or 50 millimeter over 2 hours, that changes the intensity. The intensity is what's going to change in terms of runoff, okay, and the soil saturation and so on and so forth. So you can run the model at daily or sub-daily time step. Okay, you can run the model literally for any number of years. Currently, we have data in the world for the past 100 years and the next 100 years using climate change projections, right? So you could potentially run the model for 200 years today. Okay. There are some scientists has gone back to 10,000 years back actually, looking at the paleontology actually. So they are looking at 10,000 years ago how the climate was, or 20,000 years ago what the geological shift changes happened. So there are scientists who are constructing weather data for the last 10 to 20,000 years actually. So if they have the data, then they will be able to run the model for that period. How good is the quality of the data? We don't know. Okay. SWAT is a distributed parameter model. When I say distributed parameter, not every process in the model is distributed. Okay. We still have few lumped parameters, like current number, for example. Hydrology, we use the current number technology. That current number is a lumped parameter model. Okay. It is spatially explicit or spatially distributed. Okay. Different soil, different land use, different weather, you can capture that actually. But you're not able to say exactly what's happening on that landscape. It's a lumped. All you can say is in the entire HRU, what's happening there actually. We don't know exactly what's happening, the partitioning of the different components or things like that. Okay, it is lumped. But it is spatially explicit so that you can have as distributed as you want. However you want to discretize, divide your watershed into smaller parcels, you'll be able to do that. Earlier I mentioned about the comprehensive and the process interaction. This is the key. Not every model has this component actually. So when I say process interaction, that means every equation there is a feedback into the model. So there is a checks and balance within the model. Okay. Just to give you an example, let's say you are trying to apply fertilizer, okay, to an agricultural field. In the model, I mean in the real world, people apply fertilizer to grow vegetation, to grow crops, right? Without fertilizer, there is no nutrients, that means that the crop is not going to grow. So let's assume you forgot in the model to apply fertilizer. So what will happen? If you did not apply fertilizer, your plant will not grow. If the plant does not grow, the plant is not going to put leaves. If there is no leaf, your land is not going to be covered. If the land is not covered, when there is a rainfall comes in, you are going to have more erosion. Because the plant is not taking, because unless the plant grows, it's not going to take the water from the soil. So if it doesn't take the water, okay, that means it's not growing, that means you're going to have more runoff. If it is more runoff, you're going to have more sediment. If there is a more sediment, it's going to attach more pollutant. So not applying fertilizer as an input into the model, that one input could have all this chain reaction that can impact your model output in various ways actually. So that's where the process interaction comes in actually. It interacts with different processes where it tries to capture the chain reaction that's happening of consequences of action. Okay? If you take certain action, you're going to see a consequences, right? You decided not to carry umbrella, then if there is a rain, you're going to get wet, right? That's an action. So that's the same thing actually. There is a reaction to every action here. All those reactions get feedback into the model, whereby if there is a mistake in the model input, it's going to be reflected, it's going to be shown in various places within the model output. Does that make sense? Okay. And finally, the simulation of alternative management is the key here actually, meaning running scenarios. The model can be applied, it's very, very flexible in terms of how you want to divide your watershed, for example. So here is a watershed based on the topography. Okay, here is a lake. If the lake is the end point of your watershed, it's captured everything what is flowing into the lake. That means any rain that drops within this watershed is all going to go through this river and eventually is going to reach the lake. Okay, you can divide the landscape by, you can divide the landscape by cell or sub-watershed. Cell means you just draw a grid. So each grid becomes a sub-watershed. Okay? And or you can also have sub-watersheds based on topography. So this red line that you see here, that is a sub-basin. Okay. So that means any rainfall within this red area, it all have to go through this river to this outlet only. In other words, you cannot have water, rain that's fall here, cannot go this way. It has to go by based on topography. Okay? Then we take the sub-watersheds or the cell and divide that by what we call hydrologic response unit, in short HRU. What is HRU? HRU is a unique combination of land use, soil and slope. So we take the GIS layer, the Geographic Information System layer, the land use layer, the soil layer and the slope layer, and we overlay all three maps, okay, and look at what is the unique combination of each pixel. And then we combine them together to come up with a hydrological response unit. So, meaning whatever happens in that parcel, you are going to have the same response. Okay, because the same soil, same land, same topography. So I will describe this a little bit more detail in the next slide actually. Okay. So hydrologic response unit is the smallest unit in the SWAT model, meaning that is the basic building block. If you are putting a puzzles, right, you need a basic small unit, right? So HRU. So you put together a bunch of these HRUs, that becomes a watershed. Subbasin, and the subbasins become the watersheds. Okay. So group of HRUs within a subbasin become a subbasin, and the group of subbasins will become a watershed. Okay. The SWAT model is very flexible. Let's say you don't want to use SWAT for a particular area of the watershed. Let's say this part of the watershed, you don't want to model with SWAT. You have your own measurement data. Okay? So if you have measurement data, you can simply drop that measurement data here. That means it will automatically exclude this area from modeling. You can use observed data set. Or you can also use other models. Let's say you have your own favorite model. You have your own, let's say, a forest model. And you developed a forest model and you want to take the output from that forest model and drop it in this location here, thereby everything above here is all forested land. You can incorporate other models output. Okay. So SWAT does not need to simulate everything actually, it can accept outputs from other models or observation from other places. Where it is more important is, let's say for example, you want to model the state of Sao Paulo and you have water is coming from Brasilia or from Minas Gerais or any other places. Along the border, you don't want to model what's happening in that state. You just want to drop ANA station and use that as a boundary condition. Okay. So then you can model only what you want to model, or you can model below a lake. So you know how much water is released from the lake, and that becomes the boundary condition, and you want to model downstream or below the lake, not upstream of the lake, for example. So you can customize within the watershed, you can start and stop anywhere within the watershed to model with SWAT, as long as you establish the boundary conditions. Does that make sense? Okay. SWAT is not only a non-point source diffuse pollution model, it can also handle point sources. So what is point source? Point source means municipality or industry wastewater treatment. If the city is putting out pollution and you have wastewater coming from that pollution, you can incorporate that in the model. Okay? So anything that gets directly discharged into the river, okay, this blue line that you see here, anything that gets discharged directly into the river by city, municipality, industry, mining, you can incorporate that directly in the model. Okay? So the model is both non-point and point source. So if you look at your virtual landscape, this is a, let's say this is a one landscape or one watershed. and this watershed is delineated into 3 sub-watersheds. So this could be one sub-basin, and this could be another sub-basin, and this could be a third sub-basin. Right? 3 sub-basins. So each sub-basin may have different land use. You have forest land, you may have grassland, you may have cropland, agricultural land, you may have wetlands, you may have urban landscape. So you could have different landscapes within that sub-basin. And those can be in different soils. Your forest land could be in 10 different soils. Okay? Your agricultural land could be 5 different soils actually. And some of them may be in steep slope, some of them may be in flat area, some of them in rolling plains. So the slopes can be different. Okay? So what we do here is we overlay the land use map, the soils map, and the slope map within each sub-basin, and we identify the unique combination of the land use, soil, and slope, and call it as HRU, hydrological response unit. So if you have somebody is managing a sugarcane field here, okay, that is on soil A, and the slope 0 to 1% slope, and you have another farmer growing the same sugarcane in the same soil type with the same slope. As far as SWAT is concerned, they are one virtual HRU. We do not keep this HRU and this HRU as 2 separate HRUs. They are one virtual HRU. We combine them for computational benefit. Okay? If you want to keep them separate, you need to rename them differently. You call this sugarcane irrigated. This is sugarcane non-irrigated, or sugarcane with fertilizer, sugarcane with organic input. So you need to change the land use, unique land use, if you want to capture the uniqueness in your landscape. So this is where the detail of the data set comes in. How much data do you have? How detailed is your database? Okay. So if you have a detailed land management data, you have a very, very detailed land use data set, then you will be able to capture that. So HRUs are virtual. But HRUs from one sub-basin to another sub-basin, they are 2 separate. Even though the same land use, same soil, same slope in this sub-basin, the same land use and same soil and same slope in this sub-basin, there will be 2 separate HRUs. Okay? But within that sub-basin, they will be combined. Even though they are 2 separate parcels, 2 separate land units, but they will be combined as one for simulation purpose. Does that make sense? Okay? Once all the simulations are conducted by HRU, those outputs will dump into the river and the river process takes place. The river routing process takes place. And the point source can be added at that time. So just to explain this HRU concept, let me go through one more example. Let's say this is a watershed, and this watershed has got about 20 sub-watersheds. Okay? 1, 2, 3, 4, and so on, all the way to 20 watersheds. Just let's take one sub-basin, sub-basin number 18. Okay? In sub-basin number 18, you have 28% is rangeland and a sandy soil. Okay? 51% is pasture land on a silty soil. 16% forest on a sandy soil and 4% agriculture on a silty soil. I kept it very simple, meaning one land use and one soil. I mean, you could have rangeland on 10 different soils. Okay? So the GIS will automatically capture that. The GIS will capture that automatically for you. So they can be in different slope. I'm assuming they are all in one slope here. Just to give you a simple illustration, simple example. Okay? So let's just focus on the forest. Okay, just look at the forest, which is yellow in color, the yellow color that you see here. So if I just look at the forest land, these are all the forest lands in this surface number 18. All the forest land is in the same soil, same slope. So as far as SWAT is concerned, it is one HRU. Regardless of whether that forest is here or forest is next to the river, it's the same. Within that subbasin, they are all simulated as one HRU. Okay. That means in the output, I can give you only one output for forest. I can't give you what is the amount of erosion is here, what is the amount of erosion here, or what. I cannot give you different results because they are all simulated as one HRU. But we know that is not true, right? Some forests are managed, some forests are not managed. Natural forest and plantation forest. Okay? In plantation forest, you harvest every 15 years, 20 years. So let's say you are putting eucalyptus. Every 7 years you will harvest eucalyptus. Okay? So the natural forest you do not harvest. So if I say I want to harvest my forest, it's going to harvest everything here because they are all in one HRU. There is no differentiation. Okay? So you have some riparian forest, you have an upland forest, you have managed forest, you have unmanaged forest or natural forest. Okay? So if you want different results based on how the land is managed, you need to classify your land use map like different forest types. So if you differentiate your forest types, then you will be able to capture the different HRUs. So when you run the simulation, you will get output for each HRU. Does that make sense? So that is the key here actually, trying to capture the spatial variability of your land and land management. Okay? So what do we do in each HRU? In each HRU, you get weather, like rainfall and temperature. That's going to drive your hydrology. Hydrology is also going to drive your sediment, soil loss, erosion, and that hydrology and the weather is also going to drive your plant growth, how the plant grows. Okay. SWAT is one of the very few models that incorporates plant as one of the major components. If you look at most of the other watershed models, they do not have explicit plant growth. Okay. In fact, SWAT is vegetation-centric model. That means vegetation is the center of the entire modeling system. All the feedback that I talked about is all because of the vegetation growth. And then nutrient cycling, nitrogen and phosphorus, pesticide, land management, and bacteria. So we simulate all these different processes for each HRU for each day, right? And then the results are aggregated from HRU to subwatershed, from the subwatershed to the river, and river to the ocean or lakes or whatever that's receiving that water. So that's conceptually that's how SWAT works. That's how the SWAT system will work. Any questions in this concept? Basic concept from SWAT. Yeah.
You can explain, clarify more that the vegetation and soil grids in the SWAT.
Yes. You can get, you mean when you're talking about vegetation, you can specify how much land is covered, right, by vegetation.
Vegetation cover is the one grid, and other soil What agree?
I mean, soil is where the vegetation is growing. The HRU, that's why when you overlay, we overlay the land use map on top of soil. So for this land use, let's say this is forest land, what soil it is growing. Okay? So if there are two different soils, then you'll get two HRUs. If they are one soil, then you'll get one HRU for that forest. And also, then there's a slope. If it is a flat, it's a slopey, or is it vertical? So accordingly, you'll get different HRU. So your land use and soil can be the same, but your slope can be different. Or your slope can be the same, but your soil can be different. So that's why we combine all three maps to find out what is the unique combination for all three components to represent HRU. Okay?
Professor,
Yes.
I have a question.
Uh-huh.
You can go back to one.
Slide. Yeah.
The forest is combined with different kinds of land use and soil. In this case, is
One. I'm just for simplicity, just an example. Let's assume all these are all forest land. They are all in one soil. Okay? So when I do a land management like harvest my forest land, it's going to harvest everything, including the riparian forest.
okay. But the place, the distance from the river will change the time of runoff. Okay?
Yeah.
And it is.
No, it is not. So your question is, when a land here may contribute to the river very quickly or whereas a forest that may be sitting here may take a long time to reach that water here, right? You are right, but this is the simplification in the model. Okay? You can take your subbasin smaller. You don't have to take this big subbasin.
Yes.
Okay? You can make a grid.
Yes.
Every 1 square kilometer can be a grid. Right? Then you can able to see everything is flowing in there actually. Remember, the model is a daily time step model. As long as the water comes within the same day, it doesn't matter whether they came on morning 6 o'clock or evening 6 o'clock. It's all the same time. Right?
If I need to know about this, I need to separate more.
Separate, yeah. Discretize more separations. Other questions? Okay, I'm going to switch the presentation on one other presentation so that I can. Yeah. So what I gave you so far is a generic SWAT model, actually. Okay, that's a fundamental principle of the SWAT. But now we are working on the next generation of the SWAT, which is called SWAT Plus. Okay? So what is the difference between SWAT and SWAT Plus? It is still the same thing. So fundamentally, all the algorithms, they're all same. But now we have added more flexibility in terms of how to configure the watershed, right? So previously, I'm going to give you a lot of examples here actually. Over the 30 years, we have developed this stuff and we have made a lot of assumptions and everything, and we know our model is becoming really difficult to manage and maintain. So we are rewriting the entire model again. This time we are giving you a lot of flexibility in how you can set up your model or how you can configure your model and things like that actually. And we are allowing other algorithms. Let's say for example, tomorrow you develop your own current number or a S factor and you want to incorporate that, you can easily modify one small subroutine in the model and have your own model incorporated. Now it's much more difficult in the current SWAT to do that because it's one big code actually. We are making it object oriented, make it more modular so that you can plug and play other models very easily. Okay, so that's the idea here. So that we are calling it as a SWAT Plus. And of course, there is a big team is working on that actually. When I say big team, we are talking about 2-3 people actually, not like 200 people or anything like that. It's a small team. So I'm not going to go through every one of them. I want to talk about what are we doing with SWAT Plus in general. I may touch on some of these depending on how much time I have, but I'm not going to go through. This slide is about 200 slides pack actually, so we won't have the time to go through that, but we can talk about it. All of this stuff, we have literature, we have documentation, we have manuals and things of that nature. And we may have videos that we went through all of them actually, so if you are interested in that, we can share that with you also actually. So, again, SWAT is nothing but a it's a small watershed to a river basin to simulate the quantity and quality of surface and groundwater to predict environmental impact on land management and climate. Okay, so that's in a nutshell what SWAT is all about actually. It runs still on a daily time step. It's got a comprehensive simulation landscape process and in-stream process. It's one of the largest use of the SWAT model around the world today actually. Okay. We just crossed, I know this is an old slide, we just crossed 6,000 peer-reviewed publications. Okay, 6,000. So if you want to look at another model in the same family, like the watershed model, you may be looking at maybe 200 papers. The maximum number of papers is 200. Whereas SWAT, we have crossed 6,000 peer-reviewed publications. And we have published more than 400 different journals. The model is published, all the way from social science to economists, to environmentalists, ecologists, okay? You name it, it's been used in so many different disciplines actually. That's one nice thing about SWAT is, SWAT brings in the different discipline all the way from soil science, soil chemistry, soil physics, to plant agronomy, plant pathology and like pesticides and things like that. And then civil engineers like, for example, hydrology, hydraulics, dam operations, dam management, energy management. So it definitely brings in multiple disciplines all together in one model. And we know not any one person can master all this stuff actually. Okay, so that's why a model like SWAT is really team model with a different discipline, different background. We all come together and work together to solve the problem. Okay. And we have also estimated there are close to about 8,000 masters and PhD students are using this model worldwide every year to solve a problem or to understand a problem. Okay. That's why we have this 6,000 peer-reviewed publication. I'm talking about 6,000 only in English journal. Okay, I know you all publish in a lot of Portuguese journal or Spanish journals and other journals. If you start taking Chinese journals, then you're talking about that number has exceeded more than 10,000 by now. We do have a review paper that got published by Danielle, and she has collected all the data, not only the peer review publication, all the masters and PhD dissertations, and she has documented in that paper. Actually, I mean, that paper is available on the SWAT website, and you'll be able to go there and you will take a look at that. Actually, what's happening inside Brazil, for example. So, just to give you over the last 30 to 40 years, what's happening actually, the gleams which I told you, the pesticide component, the creams is the rainfall runoff model, and the apex is the crop growth model. So we combine all those three different components. That's what we are calling now is a SWAT. Okay. SWAT is a landscape process model, and it has got both the routing and the in-stream water quality component called Qual2E embedded in that actually. And there are different versions of the SWAT model. There's a European SWAT, then SWAT for Germany, and SWAT. So there's a lot, all kinds of customization because SWAT is an open source public domain model. Okay? We do not, anybody can use this model, anybody can download it. All the source code is available for open. Okay? So what do you need in terms of climate as an input? Climate is an input into the model, right? So what kind of climate input you need? You can use precipitation, again, daily or hourly or sub-daily time, depending on whether you're going to run the model on a daily time step or a sub-daily time step. And you can have, we need a minimum and maximum air temperature. Okay. The rest of the data is optional. The relative humidity, solar radiation, and wind speed are optional input. If you have them, you can make use of that. If you don't have them, you can simulate it based on historical statistics. Because SWAT has a built-in stochastic weather generator, statistical weather generator. It can generate your weather for every day based on the last historical weather statistics. Okay. So that's what this weather generator comes in as. So the weather generator can generate all these weather variables. So if you're running a scenario, you don't care exactly, because weather or climate is a random phenomenon, right? It's just stochastic. We never know what's going to happen tomorrow in terms of rainfall. And we can predict there's going to be rain, but the intensity of the rain, the duration of the rain, the amount of rain, we don't know that actually. We'll say, roughly we can say there could be 20 millimeter rain tomorrow, but what happens, it could be 40 millimeters, okay? Depending on the atmospheric signs or atmospheric changes. So the weather generator can generate the weather statistics. It can never be able to predict exactly how much rain is going to happen, but it can say over the 30 years, the same statistics it can regenerate. Like the average rainfall, average number of days of rainfall, how many days of consecutive rainfall. Okay? All those statistics it can regenerate. So that's what the weather generator is, the stochastic statistical weather generation. So you can use this to generate this weather, or you can use the observation data set. If you have observed data set, you can know how much precipitation, how much temperature on that particular specific day of your simulation. If you are going to do calibration with the SWAT model, you have to have at the minimum precipitation and temperature, maximum temperature. Okay. If you have these data, it's great. If you don't have it, it's okay. It's not a big issue when it comes to calibration. For calibration, these two are most important. Okay. When you have a missing data, let's say you have data, but you have missing for 1 week or 1 month. Okay. You can simply put -99 in the input. Then the model will use the weather generator to generate the weather for that missing days. Then it will automatically run the model. Okay? But again, don't think the model somehow knows exactly how much rain on that day. It's a generator. It's based on the statistics.
Peter,
Yes.
weather generator is a tool inside.
Yes, inside the SWAT model.
Inside.
Yeah, but we also have the same weather generator as a separate program. It's available on our website. So if you don't want to use SWAT model, but you want just the weather generator, you can get that also.
Professor,
Yes.
the weather generator use the global information or local information too?
It depends on what you have. If you have the local information, you can generate your own weather coefficients or weather statistics. We provide the global data, right? The global weather statistics data. But you don't have to use our data. You can generate your own weather statistics. That's, say, just for Amazonia Basin. Within Amazonia Basin, you can say, just for Belize, I'm going to use this data to generate my weather. For the rest, I'm going to use the global data. You can do that too. Okay, you are not limited to use only the global or only the local, you can also have combined information. You don't, I mean, I know you don't have snow and things like that, but if you are in an area that's a lot of snow, the model can automatically convert your precipitation into snow based on temperature. You can specify at what temperature your rainfall becomes snowfall. Then it will automatically convert the data for you. Okay? So when you provide the input, you need to provide the input in precipitation equivalent. Don't give the, let's say for example, today it rained, let's say next week, I know it's not here, but let's say next week there's snow, and the snow was, say, 200 millimeter snow. 200 millimeter snow is not equal to 200 millimeter of rainfall. Okay, 200 millimeter snow could be just 10 millimeter of rainfall. Okay, so you have to always convert your snow into rainfall, equivalent of rainfall when you provide input into the model. Okay. On the landscape, on the hydrology, I mean the land process, we have, as I showed you before, you have the hydrology, the plant growth, erosion, nutrient, pesticide, pathogen. We are slowly adding, it's not ready yet, we are slowly adding heavy metal, salt is a new component we are adding in SWAT Plus. It's not there today, but it will get there eventually. Okay? And the land management is, of course, is the key here. This is on the landscape, which is the HRU process. In the watershed, in the river process, we have the instant routing, both sediment, pesticides, pathogen meaning bacteria, heavy metals, and salts. Before I continue, are there any questions? Anything else? Okay. So, the next few slides I'm going to go through to talk about the hydrology and the water quality, how it's simulated in SWAT. So, you take one HRU, right? This is a HRU where it could be have a tree or annual crop like sugarcane or corn, soybean. And then you may have grassland and so on and so forth. So when there is a precipitation, you have the soil. You can have up to 10 soil layers, 10 soil horizon. Okay, and then we have an unsaturated zone, and then shallow aquifer, and then confined layer and deep aquifer. So this is the conceptually, this is how the HRU is divided. The HRU has the plant, soil, and the groundwater process. Okay, so let's say you had a rain today. That could be rain or it could be snow, depending on the temperature. So if you have a rainfall here, that rain can be either melt if there is a snow, or it could be even irrigation. You could be applying water for irrigation from canal or from aquifers and things like that. So that rain is converted into two components actually, evaporation and transpiration. Okay, the soil evaporation, soil transpiration. Okay, for evaporation and transpiration, we use one of the three equations. You can choose which equation to use within the SWAT model. You can use Hargrave, Priestley-Taylor, or Penman-Marty. Okay. And the output from SWAT, you'll be able to get how much is the evaporation from the soil, how much is the transpiration from the plant. Okay. So you get the evaporation component and the transpiration component. Previously you used to get only ET. In SWAT Plus you'll get both separate components. Okay. So if you have satellite data to capture that, you'll be able to calibrate against satellite data on evaporation. So once the evaporation is calculated, then we calculate the runoff. For the runoff, we use the curve number technique. Okay? And the curve number is not a constant. It changes on a daily basis based on the previous 5-day rainfall event. How saturated is your soil? If the soil is highly saturated, then you'll get more runoff. If the soil is less saturated, then you're going to have less runoff. Okay? If you are using sub-daily time step, meaning hourly rainfall, then you can use the green and amp equation, infiltration equation. So the green and amp method will be able to calculate the runoff and infiltration through physical equation. In order to use the green and amp, you not only need sub-daily temperature, temperature and precipitation, you also need to have very good soil database. Soil properties is very, very important for the green and amp equation. Whereas curve number equation, you need only one soil parameter, hydrological soil group, A, B, C, D. Whereas for green and amp, you need to have pretty decent, pretty well-defined soil parameters. Okay. Once the water is divided into runoff and ET, the rest goes as an infiltration. That infiltrated water goes through layer by layer. You can have up to 10 layers. Once the layer 1 saturated, it goes to the layer 2, layer 3, layer 4, and any excess water will come as a lateral flow. Okay. So for example, if you have excess soil moisture in each layer, that water can come as a lateral flow back to the river. Okay. And any excess soil moisture also can go vertically. So it's a two-dimensional model. So it goes vertically and horizontally at the same time. And then, once the water percolates below the soil layer to a shallow aquifer through the unsaturated zone. In the current SWAT, we don't have a detailed model for groundwater model. It's a very simple, what I call bucket model. If the bucket is fills up, it goes to the next, and it goes to the next, and so on. Whereas in the SWAT Plus, we are bringing in a physically based groundwater model into the SWAT. Okay. So we are going to take advantages of that model so that it can simulate the real process of the unsaturated zone. That means you need more data. So the simplification model, you don't need data, whereas as you go into more detailed model, that means you need more data about your unsaturated zone. Okay, like the thickness of the unsaturated zone and how the transport of the water in the unsaturated zone, all those properties are required. Once the water reaches the shallow aquifer, that water can re-evaporate, capillary tension, or can return back to the river as a base flow. And it can also go to deep aquifer. All these things takes different times. So this could be in hours, this could be in several hours, this could be again hour or day, this could be several days, and this could be weeks, and this could be years. Okay. So the movement of the water is differs for different processes. They all not happen on the same day, same time. This is within one HRE. Now you think about all these HRE are different locations spatially. They also going to have its own time travel. Okay. So all these things are captured in the model actually. So once the water leaves to the deep aquifer, we generally do not keep track of this water. However, you can in the integrated groundwater model. We are also integrating SWAT with another groundwater model. So if you use that groundwater model and the surface water model as SWAT, then you can be able to keep track of how much water is going to the deep aquifer and how much of that water can be pumped back, okay, like irrigation, or municipality or industry taking water. You can run all kinds of scenarios. But in general, SWAT does not deal with this after it reaches the deep end. Okay. Next is the plant growth. So like I said, told you, SWAT has the plant growth component. The plant growth components are extremely well received, meaning it is not only able to produce what is the optimal growth, meaning that is the ideal growth of the plant. How much biomass, how much leaf it puts on, how much is the grain, fruits, nuts, whatever it's doing actually. Okay, it can able to do it using the what we call radiation interception, leaf area index, or radiation use efficiency. However, this is the ideal situation, but we know crop may not grow perfectly every year because we may have water shortage, or we may have nitrogen or nutrients, phosphorus shortage, or you may not have enough temperature to grow, or you may have soil aeration, okay, soil compaction. Okay. So all this can affect the vegetation growth. So even though this is under the ideal situation, but you are constrained by any one of these factors. So your actual yield from year to year may vary based on what is limiting, what is constraining the growth. As an output, you will be able to get how much is the stress. So when you see that in real world people are getting say 20 tons of sugarcane per hectare, and the model is saying only 10 tons, then the first thing you need to look at is what is stressing, what is limiting. Then you need to make sure your inputs are reflective, inputs are correct. Okay. Then if the reported is 20 tons and you are getting 18 tons or 22 tons, then you are within the margin of error, within 5-10% of what's observed. That's acceptable. Okay. So you definitely want to look at the stress factors and look at the amount of biomass, amount of yield, okay, to make sure they are reflective. So there are many ways to calibrate the model. It is not just only the stream flow that you need to calibrate. You can calibrate against ET, you can calibrate against soil moisture from satellite, you can calibrate against crop yield or vegetation yield or biomass. Okay. Some of them are time series data, some of them are annual average data. Okay. So you want to make sure you are right for the right reasons in all the aspects of the model, not just only one aspect, meaning hydrology. Okay. When you do that by hydrology, that means generally hydrology is only 20 to 30% of your entire water budget. Okay. Almost 60% of your water budget is evapotranspiration. If you're wrong on your evapotranspiration, you can be still right on your hydrology. That doesn't mean your model is right, especially when you're running scenarios. If you change one crop to another crop, your model may not be reflective because your ET is not correct. So it is more important, whenever I run the model, the first output I look at is crop, vegetation. So make sure the vegetation is growing and it's expected before we look at any other. You don't have to be an expert in agriculture to look at that. You need just to know enough information about how the agriculture yield, okay, forest biomass and things like that.
Professor,
Yes,
is potassium another stress, or we can get
potassium. Yeah, potassium can be a stress, but it's very potassium only helps the quality, not the quantity. Quality of the plant. Okay. Suppose if you don't have enough potassium, maybe your fruits may not taste better. But it is not going to affect the biomass or crop yield or anything like that. So in the EPIC model I showed you, it has potassium also. Okay. So the the people from Japan has got enough data on potassium, so they developed a potassium model and incorporated in EPIC field scale model. It has not gone into the watershed yet because potassium is not a health concern actually. In fact, we have lack of potassium. If people drink more water with potassium, it's okay because we need more potassium in our body, especially iodine and things like that actually. There's not enough potassium in the environment actually. Potassium also shunts the growth actually. Okay. If you look at the people's height today compared to 20, 30 years ago, we are shrinking globally. Okay. So that's because we don't have enough potassium in our water or in our nutrients. Potassium is shrinking intake. The erosion process is the key here. Actually, we use the soil loss equation, the universal soil loss equation, USLE, and we modified that using this equation here where it incorporates the runoff, the peak flow, and the area of HRU. Okay, the rest of the factors are all the same thing as universal soil loss equation, except these are all added factors. That's what makes it dynamic. Because every day you get how much runoff, right? So the USLE is not a constant. USLE normally used for annual. Okay. Here we are using the same equation, but on daily basis, using this modified that incorporate runoff, peak runoff, rate of runoff, total runoff, peak rate, and area, the size of the picture.
All the coefficient in the exponent, they
Yes.
were
Field, from
yeah.
the field experiments, yeah, from the field data, yeah. The nitrogen, I know it's a little bit busy slide. There are 4 types of nitrogen we keep track in the model. One is organic nitrogen, nitrogen attached to your soil. Okay. Then ammonia, nitrite, and nitrate. These 3 are soluble. And this is organic, meaning attached to soil particle. So when you apply nitrogen, you are applying fertilizer in the form of liquid fertilizer or in the form of solution, soluble. Or it can be manure or waste. Okay? So you can apply them, when you apply the manure, it goes to your soil and it also in the form of ammonia. Then the ammonia can volatilize as ammonia gas. Okay. Every day when there is a rainfall, when there is an exchange happening, when the plant is growing, it's going to absorb water by evapotranspiration. When it absorbs water, it is also absorbing nitrogen, soluble nitrogen. Okay. So nitrate is what is taking. Every day the organic matter can become ammonia, the ammonia can become the nitrification process to nitrate, oxidation process to nitrate, then the oxidation takes the water back to the plant. Sometimes the plant itself puts like legume crop, soybean, okay, any kind of beans, alfalfa, grass, they all can incorporate nitrogen into the soil. So the model will automatically take care of that also. Yeah. And I did not know this actually, but there is a atmospheric nitrogen actually. When there is a rain comes in, you can also get nitrogen based on the industry. When the industry releases nitrogen gas, and that nitrogen can come back to the ground when there is a rainfall, right? And that number can be significant. For example, in the US, they conducted a study in the East Coast, where there is no industry at all actually, or very little industry. The amount of nitrogen coming from atmosphere is 35%. Where is that coming from? They are all coming from the Midwestern states, like the Chicago area and things like that. That's where most of the industries. So all the emissions coming from those industries they are migrating from watershed to watershed to watershed, and then finally coming down back to the ground based on strength, soluble nitrogen. So if you don't account for the nitrogen from the atmosphere, you may significantly ignore a large component of the nitrogen balance. Okay? So you may want to look at how much nitrogen. So all you need to do is just take a rainfall sample and analyze in the laboratory. You will know how much nitrogen is in that water. Then under the anaerobic condition, under the wet condition, this nitrate can go volatilize as a nitrogen oxide or nitrogen gas, which is a greenhouse gas. Okay, this is what we are trying to eliminate for global warming. Okay, how much we want to eliminate. So if you apply that in the form of manure, you are going to have more of them. If it is soluble, they are going to be absorbed by the plant. If it is solid, it's going to get released back. And also the ammonia gas is another form of nitrogen released to the atmosphere. You also have problem with the leaching. The nitrate can leach to the groundwater. So your groundwater can get affected. So if you're going to use the groundwater for drinking purpose, and if you're applying too much nitrogen, your drinking water can be affected by excess of nitrogen. For example, in the US, in Iowa, in the 1930s and 1940s, the groundwater is clean. Okay, you can take the ground and drink it directly. Today, they are so polluted now because of all the application of fertilizers in the last 30, 40, 50 years. The groundwater is much more richer in fertilizers than what you apply on the land. You can take that water and simply apply on the land, you get enough fertilizer. You don't have to even buy fertilizer. That's how much fertilizer is in the groundwater now. Yeah. Okay. So again, you can take your groundwater and analyze it, and you'll know over the years is it continuously, steadily increasing over the period of time. Okay. And of course, when you harvest plant, when there is a runoff and sediment, you'll also lose nitrogen through that. Typically, it's about 15%. 15% of your fertilizer is lost through runoff and sediment. Okay? Because farmers is not going to apply exactly when the plant needs. They apply it hoping the plant will take it. But in between there is an environmental process like rainfall, runoff, sedimentation. They may capture as much as 15% of the total nitrogen that we apply. Okay? Next is phosphorus. Phosphorus is somewhat a little bit simpler than the nitrogen. In phosphorus, we have soluble phosphorus, nitrogen phosphate, or organic phosphorus. Soil, phosphorus attached to soil. When you apply fertilizer, manure, liquid form, they become soluble phosphorus. When you apply the solid phosphorus, solid manure, it goes to the organic. They exchange daily, and some of the soluble phosphorus can get fixed into the soil through minerals like iron, aluminum, magnesium, manganese, and things like that. Then the soluble phosphorus can be uptaken by the plant while it's growing through absorption of water. Typically, you need 1 kilogram of phosphorus for every 8 kilograms of nitrogen. Okay. If you apply in a different ratio, you will get more phosphorus staying in the soil because plant cannot take just because it's available. Plant can take at 1:8 ratio. Okay. In general, and not every plant, in general. So the problem is when you apply manure, you have more phosphorus than nitrogen. That means if the field is only organic farming and you are going to apply only manure to grow your vegetables or you are growing your crop, you are applying excess phosphorus. That means over a period of time, your soil is going to become very high in phosphorus. That's why you see all this algae in the lake is because of phosphorus, not because of nitrogen. Excess phosphorus is what's causing the algal bloom in the lakes. So when you fly over Netherlands, you will see in the summer it's everywhere green. It's not agriculture, it is all water with algal bloom because of animal manure. Okay? So animal manure is one of the biggest source of excess of phosphorus in the rural watershed. In the urban watershed, we also apply phosphorus in our lawns to maintain grasses and things like that. It also causes problems. More recently, the people in Denmark has done studies where the phosphorus is leaching to groundwater now. Denmark, as you know, they produce so much cheese and milk. They are the world number one producers in cheese and milk, right? For a country of that size, with so many cows in there, actually, it's starting to, over the last 50 to 60 years, now that phosphorus is reaching the groundwater. So in SWAT, we have modified the equations whereby you can let the phosphorus go into the groundwater. Previously we did not, now we are allowing phosphorus. If you know there is a watershed where phosphorus is going through the soil into the groundwater, you can activate that in the model. Pesticide. It's one of the most used model for pesticide registration because every pesticide needs to be registered with the environmental agency before that can be sold in the market. So there are three kinds of pesticide. There is a nematicide to kill insects inside the soil. There is a weedicide that kills the grasses. And there is an insecticide that kills the plant and protects the crop. Okay. So here we apply the fertilizer pesticide either on the soil or on the leaves. So it's depending on.
They will reach from Bahia. They have just arrived. Okay. And they will have lunch with us.
Okay. Good. So based on the pesticide that's applied, that pesticide can degrade or wash off into the ground, and that can infiltrate and leach to the groundwater. And any excess pesticide can go as surface runoff and sediment. So SWAT has got a very detailed pesticide simulation process to capture all the pesticide movement. What are some of the land management you can simulate? You can simulate crop rotations, meaning different crops in different years. Or you can have two crops in the same year, like summer crop and a winter crop, for example. Okay? You can also have different tillage operation, okay, how deep you want to disturb the soil, for example. You can have different fertilizer application, automatic fertilizer application, manure application, and you can also have time and season application, you can do that. Or you can have a continuous fertilizer application. Every time you irrigate, you can also apply fertilizer automatically. You can also have grazing, the land grazing for animals, okay. Pesticides, irrigation. You can have any source of water for irrigation. It can be pond, it can be groundwater, it can be surface water, it can be lakes, it could be deep aquifer, or it can be transported from another basin. Okay. So the source of water can be defined. You can also have tile drain system. I don't know how much of tile drain is practiced here. Tile drains are artificial pipelines under the ground to remove excess moisture. Okay. In the US, because of the snow, during the all winter, the soil is completely saturated. You can't take your tractor into the field unless you drain the water. So that's why they install this tiles or perforated pipes under the ground to remove that moisture so that they can get the tractor into the field and plant crops and things like that. So the model can simulate that. You can also have water impoundments, like you can have a dike around your field and hold the water to raise crops. like sugarcane or rice or paddy and things like that. You can implement various conservation practices, various structural practices, and you can also simulate the urban area. So they are all come under the land management module within SWAT. The next is on the in-stream process actually. How do we simulate the in-stream? So far all the things that I talked about is on the landscape, the overland process. Okay? And once all the output from the overland process are combined by HRUs, they dumped into the river, and any point source from industry or municipality is also joined. Then we look at along the longitudinal direction, along the length of the river, we look at the dilution, the diffusion, and the decomposition of the various chemical properties in the river. Okay? So we use a simple steady state model for this actually. It is not a hydrodynamic model, but SWAT has been linked with the hydrodynamic model called WASP or C=W2. These are all public domain open source models. So if you are more interested in the hydrodynamic component along the river, then there are other models that you can link up with SWAT output. Okay. SWAT itself uses a very simplified version of steady state model. Okay. So what do we do? We look at the flood routing, how much the water moves through the system, how much water evaporates, how much is the transmission loss at the bottom of the channel. Okay. And down cutting and widening, meaning the dynamic part of the thing. So for example, you may have erosion coming from upstream, coming and settling, that way it changes the depth of the river, for example. Or you may have a bank erosion that's going to widen the river. So the model is able to calculate the down cutting and widening of the river. It also estimates the nutrient transport as well as pesticide and pathogen. And more recently, we are adding heavy metals and salt in the river in-stream process. Okay. So in the in-stream nutrient, we look at what's coming from upstream sub-watershed. Okay. We keep track of 4 forms of nitrogen: organic nitrogen, nitrate, nitrite, ammonia. And we also have 2 forms of phosphorus, organic phosphorus and soluble phosphorus. And we have 2 forms of oxygen, carbonaceous oxygen demand and dissolved oxygen, and 2 forms of biology, meaning chlorophyll and algae. So this is what we keep track in the river, in every reach by reach or subbasin by subbasin. We have a water column and we have a sediment column, the bottom of the river. So the sediment layer can be a sink or a source. If there is an erosion, it becomes source. When there is a settlement, it becomes a sink. So it can either remove nutrients or it can add nutrients back to the river, depending on the velocity of the flow, velocity of the water. If it's a flood event, it can contribute. In a normal or when a laminar flow or when the flow is very, very small, it's undisturbed, then it can settle like a basin, for example. This is for the pesticide. Again, the pesticide, whatever the pesticide coming from upstream, it can degrade, meaning dilute, or it can settle, or it can resuspend from the sediment. Okay, and it can transport to the downstream. As far as the impoundment means water structures like ponds, wetland, dams, or lakes, or reservoirs. Okay, you can simulate that, so we know how much inflow coming into the water, like lakes, how much of the evaporation from the lake, how much is the seepage loss. If you have any kind of water withdrawal, you can implement that actually, how much water you are removing from the lake for irrigation, or for water supply, or for industrial supply and things like that. And then you can also control your outflow, how much water you want to release downstream. And when you want to release, you can control all those stuff with the reservoir module. The nutrient is very, very simple model today in SWAT. So if your ultimate goal is to analyze a lake water quality, then SWAT may not be the best model for that. There are other models that are better than SWAT. So you can still use the SWAT for the landscape part. Then once the water comes into the lake, there is a lake model, much more sophisticated lake model, like C equal W2. We have linked that actually, okay? So you can easily generate the input goes into that model, and then you can run that other model to look at what's happening inside the lake. Because inside the lake, we keep it very, very simple. It's like a bathtub. A big bathtub where everything gets mixed and everything is settled in a simple one-dimensional model. It is not a two-dimensional model. The major strength of the SWAT model is the upland process, where we have comprehensive hierarchical balance using physically based inputs that includes plant growth and crop yield, nutrient cycling, land management, and agricultural conservation practices, urban process, and BMP is also included. And it is very flexible in the way you want to configure your watershed. You can have water transfers, irrigation diversions, sedimentation, deposition and scouring, nutrient and pesticide transport, pond, wetlands, and reservoir impacts can be studied. Okay, that's in a nutshell what SWAT model is all about. How much time we have here? Okay, I'll have 10, 15 minutes. Before I jump in, are there any questions? That's pretty much a big picture. Yeah.
You can clarify how parts is optional. Plants need the very information to run.
Yeah, we have in our plant database, we have more than about 150 different vegetations. All the way from vegetables to annual crop to different grass types to forest types. If you don't have certain types in our database, we can work with you to develop the parameters for your vegetation. Most of these vegetations are already published by literature. Okay. So if it is a corn, it is the same corn either it's in Brazil or in the US. Only the length of the corn may be different. Here you may take 6 months to grow corn or 4 months to grow corn. There they can grow for 90 days because of the hybrid varieties. Okay. But the corn is still the same corn. Okay. So SWAT has a lot of this stuff tested already around the world, and we can continue to help to improve that and help you to parameterize that according to your local situation. Any other questions? Okay. I want to talk about the difference between those who have used SWAT versus SWAT Plus in the next 10 minutes or so. In the current SWAT, you have a watershed, that watershed divided into sub-watershed, and the sub-watershed divided into HRUs. That's it. This is what the current SWAT is. In the SWAT Plus, what we are doing is we are taking the same watershed, dividing into sub-basins. After that, within the sub-basin, you can have water area separated, land area separated. And within the land area, you can also have landscape unit. Landscape unit means upland and lowland. Okay. Riparian land or floodplain and upland as two separate components. Previously, we did not have that at all. All HRUs are mixed together within the sub-basin. Now it can be separated out. Okay. So within the landscape unit, you can have HRUs. Why we do that? By doing this, you are able to account for. Remember the previously the HRU close to the river, HRU in the upland, they are all single, one unit, right? Now they can be separated out. Okay? So it's more realistic in the simulation of water areas and the land areas. Okay. Just to give you an example, so here is a watershed, right? And that's divided into sub-watershed, so this could be a sub-watershed. Within the sub-watershed, you can have a floodplain and upland. So the HRU here does not interact with the HRU here. Okay. So you can go ahead and simulate as much as 1 square kilometer. So the first order stream, the second order stream, the third order stream, they'll be all simulated. Only the HRU within the first order streams will contribute to the first order stream. Okay. So there is no mixing of taking HRU here and the taking HRU here. They both contribute at the same time, no longer in SWAT class. Okay. So you can keep them separate. So the upland process and the lowland process. Lowland meaning floodplain. Yes.
Some papers work with recharge areas and
Recharge areas, yeah. That depends on your,
areas.
yeah. So that depends on your groundwater, meaning the below the root zone, the beta zone, or the unsaturated zone. So if it is a karst area, you may have more recharge. Okay. Whereas as you go downstream here, this could be contributing back to the river. Right? So sometimes the river brings the water back to the river. In other places, the water goes directly to the groundwater. It all depends on your soil properties and the groundwater properties. So to delineate the landscape unit, we have tested about 4 different algorithms. So what you see here, this is the automatic way of flood delineation, okay, flood zone delineation. So the topographic wetness index is what you see here. There is hit or miss. It's not always there actually. If you look at the slope position, you see that it's somewhat uniform across the plates actually. If you look at the uniform flood stage, to me it looks like too much of flood delineation, and the variable flood stage is what is this. So we did this 4 different algorithms in this paper, and we compared on the ground with the real remote sensing data. We delineated manually all the floodplains, and when we compared it, the B and D approach came more closer actually. So right now in our GIS QSWAT plus GIS interface, we are providing these 2 options for you to delineate the floodplain. Okay. And you can still control the width of the floodplain and things like that with various parameters in the QSWAT plus. So again, just to give you an idea, in the current SWAT, the conventional SWAT model, you have a sub-basin, and all the HRUs here all have one outlet only. Whereas in the new SWAT plus, you have the same sub-basin, and you have a main river. From there is a lot of tributary rivers. Each tributary river, the HRU here contributes only to that place. So the HRU here cannot contribute to this river. So it's all the local contribution only within that HRU, within that tributary contributes to the local. So the water routing takes place right from here actually. So that means only HRU here can contribute to this river. A HRU that's located here cannot contribute to this river. Okay, so we are making it more spatially explicit in terms of hydrology. And previously, you can have only 1 lake per sub-basin. Now there's no limitation. You can have as many lakes or as many ponds in a sub-basin. Previously, the lakes can be only at the outlet of the sub-basin. Now you can be anywhere in the watershed. Okay, so there is a lot of limitation that we had in the current SWAT. We are overcoming that in SWAT as much as possible. Okay. So again, I know it's not very clear, but if you look at it here, this is the main river, and these are the tributary rivers within the same subbasin. Okay? So that means a HRU here only can contribute to this river. So the HRU here cannot contribute to this one because it can contribute only to this tributary river. That is a significant improvement compared to what we had before. Okay. Another important thing in the SWAT Plus is you can send water from any HRU to any HRU, or from HRU to the river, or from river to the reservoir to the groundwater. So absolutely there is no more limitation in terms of how you want to send the flow, okay, between the different objects within SWAT. Okay. Let me explain to you in the next slide. So let's take an example, schematic diagram here. Here is a landscape. Okay, this could be an upland landscape. This could be a lowland or a floodplain. So let's say this has got 4 HRUs, 4 different land use, 4 different soils and stuff like that. And this water, only let's say the 50% of this directly goes to the river, and another about 6% goes to the subsurface, and another about 57% goes to the lateral flow. So you can control the movement of water from each HRU to other HRUs, both subsurface, lateral, and groundwater process. Okay? So this is a lot more realistic than what we used to have before. Okay? And the water can contribute to the aquifer. The aquifer can interact with each other also, and then that can interact with the river. I know it looks very complex, but it is all completely automated with the GIS interface for you. Okay? And you have always can override, or you can always change the fraction of the input that goes into various connectivity. Okay? So it's called the LSU connection file, reservoir connection file, aquifer connection file, and channel connection file. So we have 4 different connections across the different components. I don't want to go here. Okay. So this is an example of what we cannot do before. Now we can do in SWAT Plus. Is previously we used to have the reservoir only at the outer of the subbasin. You no longer require that actually. Previously you can have 1 reservoir per subbasin. Now the same reservoir can be in multiple subbasins. Okay. Previously you cannot account for what we call lakes that is local, meaning it does not contribute to the river. The water comes to the lake and disappears, right? That type of connection in the hydrology can be represented in SWAT Plus. Okay. If you don't have any water, that's fine too actually. Previously you have to have water feature. Okay, you can also represent swamp or marshland like this, what you see here, this is all marshland. Or you can have unconnected drainage. You have the river coming in, suddenly disappearing and reappearing somewhere downstream. So a lot of in deserts and a lot of the dry arid region, you have the water coming in and suddenly, like Pantano. So you don't have a defined rivers, right, in Pantano. The water goes through and suddenly disappears to the ground, and then it may reappear in another place. So those types of complex hydrology can be represented in SWAT Plus. I think there will be one more slide. I think this is not it. I'll stop right here actually. I think this is already I talked about the channel down-cutting and winding and things like that. But in a nutshell, SWAT Plus is going to be much better, but it is not quite ready yet actually, meaning the hydrology is completed, the sedimentation is completed, the plant growth is completed. We are still working on nitrogen, phosphorus, pesticides, metals, salt. So those are all the new components we are adding that's still under the development. So if you're interested only in hydrology, SWAT Plus is ready for now actually. But if you're interested in water quality, I would wait some more time actually before it's ready for water quality. Okay? Thank you.